Okay, hi Chem 1, this is Mr. Kemper, and I'd like to introduce you guys to some of my YouTube videos, and you'll be able to find them on my YouTube site, YouTube channel. And I know people are starting to get to the end of Module 3, and Module 3 involves bonding, and I think people are starting to have a little bit of trouble with Unit 3.06, so I want to give you a little lecture on how to do those kinds of things. And I'll start by sort of reviewing a little bit on the stuff you already covered before. And let's just talk about bonding in general. There's two types of bonds. Okay, there are intramolecular and there are intermolecular. Okay? You're already familiar with the kinds of intramolecular bonds. Intra means within. Inter means between. Okay? So intramolecular means within the molecule. So if I have a methane molecule, looks like this, and I know you guys have been working with these Lewis structures, okay? This pair of electrons is an intramolecular bond. It's within the molecule. Okay? And that is a pair of shared electrons. There are 4 shared pairs of electrons between the carbon and each of the hydrogen atoms. Now these intramolecular bonds are fairly strong, okay? And we've got 2 other types, or actually a total of 3 types of intramolecular bonds that you're familiar with. The first one is covalent. Okay. The second one is polar covalent. And the third one is ionic. Okay? And very simply, very basically, ionic bonds are metals plus a nonmetal. And both of these covalent bonds are 2 nonmetals. So when I have a covalent bond, that means I'm sharing electrons. And when I have an ionic bond, that means an electron or electrons is being transferred to a different atom. Remember, metals tend to lose electrons, nonmetals tend to gain them. So an example of an ionic bond would be like NaCl, sodium chloride, and that's because I have a sodium ion. Sodium loses 1 electron, and the chlorine gains 1 electron. So then they have charges on them. These 2 charges are opposite and therefore they attract each other. So that's an ionic bond. That's a really strong bond. The bonds that are shared electrons, like in methane, are still very strong, but not quite as strong as ionic. Okay? Now what's the difference between covalent and polar covalent? Well, they both mean sharing of electrons. So they're sharing electrons equally. And a polar covalent bond means they're sharing electrons unequally. Okay? So a good example of sharing electrons unequally would be in a water molecule. Water molecule is very straightforward. So that's a pair of shared electrons. Now oxygen wants that pair of electrons more than hydrogen because it's got a greater electronegativity. So that pair of electrons is closer to the oxygen than hydrogen. That gives that oxygen atom a slight negative charge. You're going to see that in your videos if you haven't already. And that leaves the hydrogen with a slight positive charge. That makes this molecule polar. So the molecule itself is polar, and this pair of electrons would be a polar covalent bond. Okay? So both of those pairs of electrons want to be closer to the oxygen than the hydrogen, and so each of those bonds is a polar covalent bond. Okay, so those are the 3 intramolecular bonds. We're going to see water quite a bit in the videos. So that's just a real quick review of the different types of intramolecular bonds. I want to talk right now, though, about these intermolecular bonds between the molecules. These kinds of bonds are what hold molecules to themselves, or another one like it. So let's get rid of all this stuff. And on the other board I've got here the types of intermolecular bonds or forces, and you're going to encounter those in section 3.06. Okay? So the first kind of intermolecular bond is a dipole. So let's look at that. A good example is the HCl molecule. Okay? So if I look at the Lewis structure, I'm going to have non-bonding pairs of electrons around the chlorine, and then a shared pair of electrons between the hydrogen and the chlorine. So that's the Lewis structure. Now, if you look at the electronegativities, that's the desire of an atom for electrons. This pair of electrons will be a little closer to the chlorine, so that will make the chlorine a little bit negative compared to the hydrogen, which is a little bit positive. Okay. Now, if I bring another, I'm going to get rid of this and put it on top actually, make it a little easier to see. So this will be slightly negative, slightly positive. I'm going to bring another one of these HCl molecules up close to it, and it's going to orient like this. Why would the chlorine be opposite the hydrogen when they want to attach to each other? Well, remember, this chlorine is going to be slightly negative, and this hydrogen will be slightly positive. As a result, this chlorine from this molecule will be attracted to the hydrogen of the other one. And so I'm going to have an attraction between those two molecules. Same thing with this hydrogen, which is slightly positive. That chlorine is slightly negative. So I'm going to have an attraction between the two molecules. Those orange bonds, which I'm going to use, are intermolecular bonds. That will connect a HCl molecule to another HCl molecule. So what I've just created would be a liquid. If I have just individual HCl molecules floating around, that'd be a gas. As soon as they start making these intramolecular attractions, then we can call it a liquid. Okay? So that's an example of a dipole intermolecular bond. And as you see in the videos, a dipole simply means two poles. One side of the molecule slightly positive, one side of the molecule slightly negative, and those two poles are going to attract the opposite poles of a different molecule. Okay, so that's our first type of intermolecular bond, it's dipole-dipole. Okay? Second one is going to look very much like it. And we're going to look at hydrogen bonding. Okay? Hydrogen bonding involves, I'm going to call it super dipole. It's going to look a lot like what I just talked to you about, but they're extra strong, and we'll figure out why. So let's look at a water molecule, which we already sort of drew. Okay, and remember, the hydrogen is going to be slightly positive, and the oxygen slightly negative. Okay? Now, because oxygen is very electronegative, that pair of electrons is going to be very close to the oxygen compared to the hydrogen. And so really, we can make this a extra big partial charge. Okay? And this will be an extra big positive charge. Okay? So if I bring another water molecule close, how will it orient? Well, let's see what will happen. So there's another water molecule I bring up close. And remember, this hydrogen is slightly positive, slightly negative for the oxygen, slightly positive for the hydrogen. So I'm going to get an attraction between the hydrogen of this molecule and the oxygen of the other one. And so that's going to be our intermolecular bond. Same thing will happen between the oxygen of this one and the hydrogen of that one. So these orange colors are the intermolecular bonds. Now, that looks a lot like the last one I did, right? Well, remember, because oxygen is so electronegative, this partial charge is going to be extra big. Add to that the hydrogen is super tiny, so that hydrogen can get really close to the oxygen. So this bond, this intermolecular bond, is extra strong. And so that's why I call it super dipole-dipole. Okay? Now, when we break these bonds right here, that's what changes water from a liquid to a gas, or from a solid to a liquid. Okay? So they're extra strong, and this gives rise to higher boiling points. If I have really strong intramolecular forces or bonds, that means it's hard to break them apart, which means I get a high boiling point. So water has a very high boiling point relative to the HCl molecule that I showed you before. Water's boiling point is about 100 degrees Celsius. HCl's boiling point is, I think, about minus 35 degrees Celsius, so way below zero. It's already turned into a gas. Okay? So hydrogen bonds are extra strong dipole-dipole. Okay? The next one we're going to call London dispersion forces. And these are a little strange. We're going to call this LDF for short. And these kinds of forces are temporary, weak, and easily broken. That's why we call it the Hollywood bond. I didn't make that up, but that somebody did, thought it was funny. Okay, so let's talk about how that forms. So these kinds of bonds are intramolecular as well, and they're going to be between noble gas atoms and nonpolar molecules. So a noble gas would be like helium, neon, etc. Nonpolar molecules would be like a chlorine attached to a chlorine, or an iodine attached to an iodine. So those are nonpolar because neither one of those atoms wants that pair of electrons any more than the other, and so they're shared perfectly evenly. That results in a nonpolar molecule. Okay? So how do these forces appear? How do these molecules stick together if there's no side that's partially positive or negative? Well, let's look at a helium atom. I've got two protons in the center, and does it make sense that possibly I've got those two electrons maybe on one side of the atom at any given time? So helium atom's got two protons, two electrons. We don't know where those electrons are, but it's certainly possible that they could be on one side of the atom at a given time. So let's look at another helium atom. Now, this helium atom's also got two electrons. What do you think these two electrons will do to the electrons that are in that helium atom? If you said it will repel them, you're right. So maybe those two electrons get pushed to the other side temporarily. So look at what's happening. I've got these two electrons staring straight at that positive 2 charge of the other helium atom. And that creates what we would call a temporary or an induced dipole. Okay? So there's a weak attraction there between those two helium atoms. That is what we call London dispersion forces. That's that temporary weak force. It's the weakest of the intermolecular forces. Now, if I took a different noble gas, say neon, neon's got a lot more protons in the center and a lot more electrons, so this bond will be a little bit stronger between the two neon atoms. And as it turns out, if I go down the group of noble gases, those intramolecular forces, those temporary intermolecular forces, London dispersion forces, get stronger and stronger. And so there's a nice trend that the boiling points going down the group from helium to neon all the way down to xenon, the boiling points get higher as well. It gets harder and harder to boil those substances. So this is a London dispersion force, and that would also hold, say, two chlorine atoms together. So if I have two chlorine molecules, okay, remember those are nonpolar, and I could have the same setup as I did here, where I would have these weak intermolecular attractions. Okay, so these weak intermolecular attractions that are only temporary we call London dispersion forces, and that happens with any nonpolar molecule or any noble gas. So the order of strength of these intermolecular forces, hydrogen bonding, is highest. That's greater than dipole-dipole. And that's greater than London dispersion forces. So that's sort of the order of intermolecular forces. These forces are only 1% as strong, okay, as intra-molecular bonds. Okay, so when we boil something, what we're breaking is these intramolecular bonds. We're not breaking the intramolecular bonds. So when we boil chlorine, we're turning it into a gas. So we're breaking these bonds, not the bonds within the molecule. And that's really important to understand. That when I boil water, I'm not breaking the, let's draw this. When I boil water, I'm not breaking these covalent bonds. I'm breaking those intramolecular bonds that are between the two water molecules. So again, if I have something set up like this, the intramolecular bonds are the orange ones. Those are the bonds that I'm breaking when I boil water, the orange ones. The ones between the molecules, not the ones within the molecule. That's a really important idea to have in your head, okay? And I'm just checking how much time I got, a couple more minutes. The last thing I want to talk to you about is what your videos talk about, something called ion dipole. Okay. And this type of intermolecular bond is basically how something like salt dissolves. So let's go back and look at a sodium chloride unit, okay? And then let's bring a water molecule up close here, okay? And let's bring another one over here. Okay? So a sodium chloride unit or molecule has ionic bonding in it. So these are full +1 and -1 charges. And then we've got these water molecules that we know that the hydrogen is a slightly positive charge and the oxygens are slightly negative. Okay, so what we've got here is an ionic molecule and a polar molecule. So remember, these bonds right here are the intramolecular, and what we're going to show is the intermolecular. Why does water dissolve salt? Well, you can see that the positive ion, sodium, is going to be attracted to the oxygen in the water molecule and form this attraction. Same thing will happen between the hydrogen and the chlorine, and it will happen with lots of different water molecules. Okay, so there's going to be all these attractions, and eventually these water molecules will pull apart that sodium chloride unit. So these are called ion dipole attractions. Remember, water has a dipole. Again, real quick, let's look at a water molecule. Slightly positive, slightly negative, and I can draw a line between the molecule, or within the molecule. One side of it's slightly negative, one side is slightly positive. So we call that molecule having a dipole, two poles, one side positive, one side negative. That allows water to do amazing things like dissolve salt, dissolve sugar, lots of other things. Okay? And it also results in very high boiling points for things that have hydrogen bonding. So elements that can hydrogen bond, you will have an oxygen, nitrogen, or fluorine attached to hydrogen. So the most common molecules that can hydrogen bond are water, ammonia, and hydrogen fluoride. Notice each one of them contain hydrogen, okay, for hydrogen bonding, and they contain the three most electronegative elements: oxygen, nitrogen, and fluorine. Those are the molecules you're going to see most commonly that will be able to hydrogen bond with intermolecular forces. So I hope that helps. I'll get back to you with more videos in section 8 that will sort of build on this.